Before we get into the examples that I've got in this lesson, I think it would be good to discuss what an ionic equation is and what an ionic equation actually shows. An ionic equation is a stripped down version of a full stoichiometric equation, so there's just a regular balanced equation, because in a regular balanced equation, there is no overall charge. So everything on the left you will see is neutral, zero, and everything on the right is also neutral as well. Whereas in an ionic equation, it only shows the ions that are actually participating in the production of product. And there will be charged species on the left as well as on the right. And what makes them difficult sometimes is not only do you have to make sure the atoms are balanced on the left and the right, but the charges have to balance as well. An ionic equation shows something being oxidized and something being reduced. Now, why am I saying this? Well, when something is being oxidized, electrons are removed from that species. They're kicked out, if you like, using that analogy. And you will see that the electrons, they must appear on the right-hand side of the equation. Whereas when something is being reduced, in other words, it is gaining electrons, the half equation will show electrons on the left-hand side. So this comes back to something you would have learned in, lower level chemistry, this idea of oil rig, where oxidation is loss of electrons and reduction is gain of electrons. So it's just applying that. So we're going to put these definitions into use now in the second part of this question. So aqueous ferrite ions decompose in the presence of hydrogen ions, so that would be H+, forming iron 3, oxygen and water. Construct the ionic equation for this reaction. So let's go ahead. So we have Fe(O4) 2-. It says it's reacting with H+, and the products are Fe3+, oxygen, remember oxygen is diatomic, O2, and water, H2O. So you will see that neither the charges are balanced. We've got a 2- on the left and 3+ on the right. And the atoms are not balanced either. So that's what I need to balance next. Let's start with putting a 2 in front of the H2O to make 4 oxygens. And then to make the hydrogens correct, we can put a 4 there. Let's just do a quick check. So we have 1 ion on the left, 1 on the right, 4 oxygens on the right, 4 on the left. So that's fine. 4 hydrogens on the right, 4 on the left. And so the atoms are balanced. Now let's take a look at the charges. So we've got a total of 3+ on this side. And on this side, we've got 2- and 4+. So that gives us +2. So this equation is not correct because the charges don't balance. To get these charges to work, to get them to balance on each side, we need to try different stoichiometric balancing numbers before each species in the equation. So now we have our final answer. 2 Fe(O4) 2- plus 10 H+ goes to 2 Fe3+ goes to 1.5O2 plus 5H2O. So not only is it atom balance, that would be your first tick, check that, it is also charge balanced as well. Let's get on to the second part now. The half equation for the reduction of iodate 5 ions is shown below. Iodate 5 ions oxidize iodide ions in the presence of acid. Construct the ionic equation for this oxidation. So before I can actually construct the ionic equation for this reaction, I need to construct another half equation. So let's go back to what I said at the top. In an ionic equation, you must see two things. Something is oxidized and something is reduced. As we can see, if you look at this equation, you can see the iodate is being reduced. This is the rig part of it, if you like. That's the reduction part. So now we need to find an equation for the oil part. Oxidation is lost to something being oxidized before we can construct and add those two half equations together to make the full equation. So the oil equation is going to be I minus goes to I2 plus E minus. and then I need to simply balance the half equation. So now I have the half equation for reduction and the one for oxidation. I can go ahead and add those two half equations together to create the overall ionic equation. Now, to balance half equations, you need to make sure the electrons, which I've circled here, are the same in each equation. What you have to do is multiply either one or both of the half equations through by a number to change the electrons to make them exactly the same. So what do? I just multiply the whole thing through by 3, which will give us 3 times 2 is 6i minus, goes to 3i2 plus 6e minus. So now I'm going to be adding this equation to this equation. Adding the two half equations gives, and by the way, you literally add everything on the left and then everything on the right, just like a maths equation basically. So I'll put like a plus sign there. It's going to give us, the next thing to do is to cancel down things that are common to the left and the right hand side. So they must be exactly the same to be cancelled out. So I know the electrons are going to cancel out because I made 6 electrons previously. The next thing is I can see there's an I minus on the right hand side and there's a 6i minus on the left. So I can cancel one of them with the 6. So that's going to become 5. And a quick check shows there's nothing left there to cancel. So the final answer will be, and that's it. Now, remember what I said above. I have to make sure that the ionic equation is both atom balanced and charge balanced. So I can see that on the left-hand side, the total charge is 0. There's no charges on water or iodine. So let's check the left-hand side. So we've got 6 plus, negative 5 there, and negative 1 there. Well, negative 1 plus negative 5 is negative 6. Negative 6 plus 6 is also 0. So I know that the charges are balanced. And then the atoms, 6 iodines on the right, 6 on the left, 6 hydrogens on the right, 6 on the left, and then 3 oxygens. So the atoms are balanced as well. If you have any questions, comment down below and I will get back to you. Otherwise, thank you for watching and I will see you in the next one.